In today's discussion, we're diving into something fascinating. Did you know that the rules that guide tiny particles are the same ones shaping our everyday world? Yes, the common sense way we see things actually comes from these tiny particles behaving in very unique ways. It's quite surprising but true.
Exactly. And because of this, understanding these rules has become very important. Think about quantum computers. These devices work because they use this strange behavior of particles. Quantum mechanics isn't just for talking about atoms in a lab anymore. It's also about real-world technology.
When I first learned about quantum mechanics, it was all about historical experiments and models. We studied the photoelectric effect and the Bohr model. Niels Bohr's early atomic model was like a cartoon solar system. Electrons were thought to orbit a dense nucleus, much like planets around the sun. But this simple image wasn't perfect. Bohr's idea was a step to understanding atoms better. It showed that electrons could only occupy specific energy levels, or orbitals.
Understanding these early models, like Bohr's, helps explain the evolution of quantum mechanics. Initially, scientists thought of atoms in clear, classical terms. Yet, it became clear that this wasn't enough. Bohr introduced the concept of discrete energy levels, where electrons wouldn't radiate energy as they moved. These orbitals were a breakthrough. They allowed physicists to make sense of atomic spectra. The model wasn't perfect, but it shaped how we view atoms.
The early days of quantum mechanics were filled with challenges and confusion. Many great physicists struggled to understand this counterintuitive picture. Charged particles moving near each other should radiate energy and become unstable, yet they didn't. Because of this, the teaching has shifted over the years. Instead of focusing on early confusion, we start with the theory as we know it today. This gives students a clearer understanding from the beginning.
It's crucial to start with a strong grasp of the historical context when learning quantum mechanics. By understanding where the ideas came from, the subject makes more sense. We see the progress that has been made and appreciate the current understanding. While the teaching focus has evolved, knowing the history helps us grasp why things are the way they are now. Early experiments laid the groundwork for today's advancements and understanding.
Let's talk about the concept of spin. It's a lot like flipping a coin. In the real world, a coin shows heads or tails. But in the quantum world, things are different. A quantum coin can be both heads and tails at the same time. This is what we call superposition. At first it sounds odd, but it's a normal part of quantum mechanics. It shows us how unique the quantum world is compared to what we usually know.
Superposition is indeed a strange idea, but it's a real description of how things work. Unlike in the classical world where probabilities show our lack of knowledge, in quantum mechanics, probabilities are built into the theory. When you think about a weather forecast, probabilities mean we don't know some things. But in quantum mechanics, these probabilities are essential and reveal a new layer of understanding.
In quantum theory, these probabilities are not about our ignorance of reality. They are about the reality itself. It's like saying that nothing is certain until we observe it. This is one of the biggest differences between the quantum world and the world we see every day. Intrinsic probabilities change how we understand everything at the smallest level and add depth to the mysteries of quantum theory.
Indeed, the idea of superposition and these intrinsic probabilities presents an intellectual challenge. It pushes us to rethink our ideas of reality. It's why quantum mechanics is both fascinating and puzzling. Many confusions stem from this, as it challenges the way we think about particles and their behaviors. Still, these concepts are essential in helping us unlock the secrets of the quantum world.
Now, let's imagine a very curious experiment called the double slit experiment. First, you have an electron gun. It shoots electrons towards a barrier, and this barrier has two little openings in it, called slits. Behind this setup, there is a screen to catch the electrons. If electrons were just tiny particles, like little bullets, we would expect them to go through one slit or the other, hitting the screen in separate spots.
But when scientists actually did this experiment, they saw something quite strange on the screen. Instead of two spots, there was a pattern of stripes. Some areas on the screen had lots of electrons, while others had none. This is similar to what happens when waves pass through the slits and make a pattern. Imagine waves on water. They can meet and cancel each other out or make bigger waves. This is what causes the pattern.
The most surprising part comes when you send just one electron at a time through the slits. You still get the same striped pattern on the screen. It seems like each electron is not just acting like a tiny particle, but also like a wave. Scientists think the electrons are exploring both slits, not just one, as if they are taking more than one path at once. This is a very different way to think about how particles move.
Famous physicist Richard Feynman had an interesting way of explaining this. He suggested thinking of all possible paths an electron can take as tiny clock faces with hands pointing in different directions. When we add all these paths together, they explain why we see the pattern on the screen. The math works out beautifully, but what it truly means for reality is still mysterious. It's both simple in math, yet complex to understand.
So, when we think about electron paths, it's really curious. The electrons seem to explore multiple paths at once. They're not just choosing one path to the screen. This idea, while mathematical and fascinating, is also quite puzzling. The calculations prove it works, but does that mean it's real? The beauty lies in how this theory can explain what we see, even if it's hard to imagine in everyday life.
That's the intriguing part of quantum mechanics. It's where the philosophical ideas meet practical use. For decades, the way we look at this has changed a lot. It's not only a mental exercise anymore. Understanding these strange realities helps us with technology. We used to think it didn't matter much in the real world, but now it has direct applications, especially with technology today.
These concepts are becoming more relevant as we advance. The connection between the philosophical side and the tech side is more apparent today. We can see how the strange nature of quantum mechanics influences the technology we create. It's fascinating to see how what once seemed abstract research now fuels innovations that shape our everyday life. It's a blending of old theories with new practical outcomes.
Exactly. These days, the understanding of the quantum world affects how we develop technology. It's not just theoretical anymore. It has an impact on how we approach problems and create new solutions. By exploring these quantum realities, we gain a broader perspective on their potential. This helps us realize how much more there is to learn and use in the future.
So, moving forward, let's talk about quantum computers and qubits. Have you ever heard of qubits? They are quite special because they are different from the regular bits in normal computers. A bit is usually just a 0 or 1, but a qubit can be both 0 and 1 at the same time. This is possible because of a property called superposition, which we learned about earlier. Electrons, for example, can be qubits because of their spin, which can be up, down, or both.
Exactly. And another exciting thing about qubits is entanglement. This is when two qubits become linked in such a way that the state of one affects the state of the other, no matter how far apart they are. Imagine having one electron here and one far away on another planet. If they are entangled, changing the state of one, like measuring it, will instantly affect the other. This is known as the Bell state, and it is truly mind-boggling.
Entanglement is vital for quantum computing because it enables complex calculations. But the concept is also intriguing due to the worries it caused for physicists like Einstein. He called it spooky action at a distance. Some thought there might be hidden variables explaining it, but experiments showed that is not the case. The system works as is, with qubits interacting in ways we are still learning about. Entanglement leads to faster problem-solving in quantum computers.
As quantum technology advances, we can use more qubits to handle bigger problems. A few qubits can do things impossible for classical computers. With each extra qubit, the complexity grows incredibly fast, doubling the possible states. Imagine now a machine with hundreds of qubits all working together. This means we can tackle tasks like never before, making quantum computing a field full of promise and potential as researchers continue to build on this foundation.
As we look forward, it's exciting to consider how quantum computers could scale up. Imagine having systems with 100 to 500 qubits. These systems can handle problems much bigger than we can solve with our current computers. With each new qubit added, the potential solutions multiply at a rate faster than we can easily imagine. This opens up new possibilities, showing just how powerful these quantum systems can become.
Absolutely. The quantum world's complexity is astounding when you think about it. A system of hundreds of qubits has more possible states than there are atoms in the entire observable universe. This kind of power and potential could revolutionize fields like medicine, cryptography, and beyond. Advanced quantum systems might help us solve problems we currently can't even define clearly. It's a huge leap forward in computing.
Building such large quantum systems isn't without its challenges, though. We need to find ways to control and maintain these delicate quantum states. These environments must be incredibly stable and protected from outside interference. Yet the feasibility is within reach as more researchers focus on overcoming these hurdles. Seeing a functioning quantum system with hundreds of qubits within the next decade is a real possibility.
Yes, and as we overcome these challenges, quantum technologies will play a big role in our world. Imagine quantum computers being as common as today's smartphones. They could solve complex calculations quickly and change how we approach tasks in many industries. Our future might see these technologies deeply integrated into society, enhancing everything from healthcare to climate modeling. The journey is just beginning, and the impact could be immense.
Please like and subscribe if you enjoyed our discussion today. It's important to stay informed about technology as it changes so quickly. Your support helps us bring you more interesting insights into the world of quantum mechanics and beyond.